Okay, so we looked at aqueous reactions, which are really easy to determine the change in enthalpy by measuring the temperature taken up by the surroundings, which is essentially water. But not all reactions take place in an aqueous solution, right? So we have a lot of combustions. There's a lot of hydrocarbons, and if you think back at the beginning of the lecture, we were actually looking at ethanol ice cubes, right, that were burning, and you cannot really measure the heat that's given off because the surroundings are air, and plus we have another problem here, right? So let me write that reaction. So here's ethanol, and it reacts with oxygen in a combustion to form water and carbon dioxide. And so every time you are evolving gases, you might also be doing some sort of work, right? So you get going back to the original equation here, the change in energy is equal to not just the heat, it's also equal to well, plus the work. It's heat plus work, which we don't really do a whole lot of work in a beaker full of water, where our system is the reaction and water are the surroundings. So that's most of the heat is going to be taken up by the water, and so we can eliminate W here, but W is always has to be taken into consideration if we're looking at a combustion reaction or anything that's not done in an aqueous solution. So one of the examples that you can probably relate to is a combustion engine. So here you're given a piston here, and you're burning some sort of gasoline, and the gas that's expanding is working on the cylinder. So you're doing some work here and ultimately moving the car or the vehicle, whatever it is. But so what we can do with W here, we can work out W by saying W is equal to force times distance. We know this already, and I'm going to write down the units just because the unit game is actually really important to make sure that we end up with joules. Okay, so a force is of course a kilogram times meter per second squared. You can think of it a force like acceleration. So you've got meters per second, which is a speed, and so if you accelerate, you get meters per second squared, and you have to have some sort of mass there for it to act as a force, right? And so that force works on a distance. It pushes something forward, and that's also in meters, and so this is how we get the units of joules: kilogram times meter squared times second squared. We can also think of force as some sort of pressure, that there's a force acting on an area, right? So think of a hot air balloon or any kind of a balloon where you have gas molecules that are moving around in a balloon, and they hit the inner surface of the balloon. So that's a force, those molecules bouncing depending on the speed, on the kinetic speed. And so that's a pressure, right? So you've got air. That's usually what we think of pressure, air pressure, but it's actually a force that's acting on an area. And if you look at those units, they turn out to be uh, uh, not joules, but so you have a force that's kilograms times meters, just a meter, per second squared, and that's acting on an area, right? So area is length times length, and if you measure that in meter, it would be meters squared. So that meter would go away, and you would have kilograms per second squared per meter. And so you can now substitute that. You can solve for F and then substitute that, and what you would get is W equals pressure times area times distance. And so again, using those units, kilograms per second squared per meter, which I determined here for pressure, then times the area, which is meter squared, and a distance is meter, and so meters cubed is a volume, and so we can also determine the volume of this particular problem here as a piston, because we're only changing the height. The cylinder is the same, has the same area here, right? And so you can determine the volume, the change in volume, by using the area, so this area here of the circle. So it's just the volume of a circle is the area times the height. Okay, so the change in height. So this is, if this goes up by that distance here, all we need to do is take the area times the change in height. And so that's the same thing as delta V. So we are really substituting area times distance or height in this case with delta V, and we still have P here. And the reason this formula turns into has a negative P delta V is because it's doing the work done on the surroundings, right? And so the work done on the if you want to have the work done, it's an expansion, so it has to have a positive delta V, right? An expansion, but that means it's a negative. It's giving off the actual reaction. The expansion is giving off energy, so that's why that negative sign is there. And of course, usually volume is measured in liters and ATM, and we have to then, if we plug this into this equation, we use ATM for pressure and liters for delta A. In order to get back to W, we're going to have to convert the atmospheres times liter with this conversion factor. So this is an important conversion factor. Let's use that equation. W equals minus P times delta V to determine work. To inflate a balloon, you must do a pressure volume work on the surroundings, right? So if you're inflating a balloon, you're gonna have an increase in volume here. In this case, it's 1.75 liter increase from 0.5 to 1.85. That's delta V. And if you do that against an external pressure of 1 atmosphere, you can easily calculate that probably in your head. 1 times 1.75, right? So you have 1.00 ATM, and let's not forget the sign, so this is going to be negative, times 1.75 liters gives us 1.75 ATM times liter. And if I wanted to convert that to joules, I need to do 1.75 ATM times liters. I need to use this conversion factor here from the other page. 101.3 joules equals 1 atmosphere times liters. So I multiply by 101.3 joules divided by 1 ATM, and that's simply going to give me 177 joules. So these problems are actually pretty simple, and I'll just work one. Okay, getting closer to where we really want to go, and this is just a summary of it. So what we know now, we have a really good grip on how heat is exchanged between a system and the surroundings. Heat and work are both parts, both ways of how energy can be exchanged between two systems. And if what we're after is the change in energy, and we can keep the volume constant here, right? So then I don't have to worry about W. So that would be really convenient if we could simply keep the volume constant, right? But then and then you end up with the delta H of the reaction is equal to QV, which is heat when the volume is kept constant, but we also want to keep pressure constant, right? So if you want to, and the reason for that is I want their delta H, which that's a new symbol now. Delta H is specific to a chemical reaction, right? So enthalpy is heat associated with a chemical reaction. So that's really what we want. We don't just want the change in energy. We want the change in energy that's specific for the reaction. And if we keep volume constant and then also pressure constant, so then that goes away, we can say that delta H is equal to negative QP, P meaning here pressure kept constant. And that's usually done in a bomb calorimeter, of which we have, we'll see look at a picture here in a minute. So, and then we can, so again, enthalpy is extensive property of a substance used to obtain the heat absorbed or evolved in a chemical reaction. So delta H is equal to the Q, negative Q here, right? And there are tables in the back of your book of these types of enthalpies. And similarly to energy, it's also in altitude, it's also a state function. It's always specific. It doesn't matter how you got there, right? If you break the bonds of ethanol and you make carbon dioxide and water. It doesn't matter how much heat you stuck in there. The only thing that matters is the difference in energy from the ethanol to the water and carbon dioxide. So we can do reactions, we can do calculations specific to a chemical reaction, right? So this is a neutralization reaction that we looked at in the beginning of lecture 2. HCl and sodium hydroxide can be neutralized to form water and sodium chloride, and this is an exothermic process. The heat is given off, and so if I add 55 milliliters of 0.5 molar solution HCl to 45 milliliters of excess, right? So then I know that my limiting reagent is going to be the 55 milliliters of 0.500 molar solution. From that I can calculate the number of moles, and if I can calculate the heat that's given off by those number of moles, then I can calculate delta H for this reaction. I can scale that up to one reaction, where this is easy because it's all 1-to-1, 1 mole. So for one reaction, and let's just do this, and it's done in a coffee cup. You can simply say that you have 55 milliliters and 45 milliliters added together. That makes it 100 milliliters. Again, you can argue that you probably have 95% of it as water, so that 100% of the solution will have an equal specific heat capacity of that of water. So we're going to use 4.18 joules per gram per degree, and we can look at the change in temperature of the solution and then calculate Q, and then also relate that to the number of moles. So now I have, because I need room, I need to have a blank page. So, but what we have is we have 0.055 liters of HCl. That's our limiting reagent, and the molarity is 0.500 m. So this is 0.0275 moles of HCl. So whatever Q is given off by this reaction and taken up by the water, by the 100 milliliters here. So Q for the solution can be calculated. That's going to be driven by 0.275, and then I can scale that up. Okay, so we have 100 grams of solution, which is the 55 plus the 45. We're going to assume, and that's a really good assumption, that the specific heat of that solution is equal to that of water, because it's more than 95% water per gram per degree. And the change in temperature was 6.8 degrees. I'll go back here. It went from 25 to 31.8. So that's 6.8 degrees. Degrees cancels, grams cancels, and we get 2,845 joules, or if you wish, 2.845 kilojoules. And that's, we can set these two equal. That's given off for 0.027 moles, so that becomes a conversion factor. 0.0275 moles of HCl is equal to 2.845 kilojoules. This is a conversion factor, and if I want to know the molar heat capacity or the delta H for the reaction, I need to scale this up to 1 mole. So I can easily do that by saying that delta H of the reaction is 2.845 kilojoules divided by 0.0275 moles. And that gives me, and what I didn't put in here is, of course, that this is an exothermic reaction, so I need that negative. 104 kilojoules per mole is the delta H of the reaction, right? So this is of course Q for the solution for water, right? So that's going to have a positive number. But what I need to do is I need to change that to a negative number because the heat absorbed by the water is the heat given off by the reaction. So I needed to put a negative value in there, right? So this is where this comes from. So I can calculate molar heats based on these types of measurements. Okay, so here it is all worked out one more time for you to see cleaner than with my handwriting, right? And so we write these reactions like that. We then put, right, we put the balanced reaction there, and then we simply write delta H equals minus 103.4 kilojoules, which means if you have a minus, it's part of the product. If this was a positive, it would be part of the reactant. So it's much easier for us to simply write delta H equals whatever it is next to the reaction instead of putting that inside of as a reactant or a product. And so a positive sign again means it's on the left side. A negative sign means it's on the right side. All right, so we can do even better than doing it in an aqueous solution. We can use a calorimeter, and then your calculations become very simple. It's a contained. You can even use a styrofoam cup. You're going to contain most of the heat loss there. But we have these sophisticated bomb calorimeters. I'll go straight to the picture here, right? With very strong metal walls, and you can fill this up with water, and then inside you have a calorimeter, and this is for combustion reactions, right? You can supply that with oxygen here. The inside chamber is full of oxygen, for example, and then you weigh out I don't know, 14 grams of coal or charcoal or something that you're combusting, whatever it is. Even liquids like 50 milliliters of ethanol can be placed there. And then you can, of course, you can measure the temperature with a thermometer. It's pretty simple here. And then you ignite it, and heat's given off, and you can measure the heat given off by this reaction, and then knowing what the heat capacity is of the calorimeter, so you don't even have to worry about the volume in here. You can just give this there's a specific constant for different kinds of calorimeters, and so the units are in kilojoules per degree, so you don't have to per gram, so that makes it a lot easier. And so looking at those units, all you have to do is multiply the heat capacity of the calorimeter by the change in temperature, and you can determine the heat absorbed by the calorimeter. And we can do the same thing here that we did for the solution, except now we're going to do it in a calorimeter, right? So we have 0.01 grams of sugar, and we burn it in a bomb calorimeter. And then the temperature goes from 24.92 to 28.33. So that's an exothermic reaction, right? The calorimeter gained heat, the reaction lost heat. Find delta H for the reaction for this combustion. The heat capacity of the calorimeter is 4.9 kilojoules per degree. So that makes it actually pretty simple. So Q for the calorimeter is going to be equal to 4.90 kilojoules per degree Celsius. We take the difference between in temperature there, which is just 3.41 degrees Celsius. We get 16.7 kilojoules. Okay, now Q of the reaction is going to be equal to a negative Q of the calorimeter. So now I know that we have minus 16.7 kilojoules for whatever that is, moles. And so I can calculate that. So 1.010 grams of C12H12O11 times 1 mole of C12H12O11 divided by its molecular weight, which happens to be 342.3 grams of C12H12O11 equals 0.00295 moles, let's just say sugar, same thing. And so we can get delta H for the reaction. So it's going to be this number here, minus 16.7 kilojoules divided by the number of moles, 0.00295 moles equals negative 5.66 times 10 to the 3 kilojoules per mole. So 1 mole of sugar has quite a bit of energy in it, and it releases that, right? So, and that's kilojoules, 5.66 kilojoules per mole. All right, let's take a break. And when I come back, we're going to look at these chemical equations and delta H's.